Hello, I'm Kumpei Ogawa from Tohoku University, Japan. I'm going to present our paper, Redirected Drawing, Expanding the Perceived Canvas Size in VR. This study was also done by Kazuyuki Fujita, Kazuki Takashima, and Yoshifumi Kitamura. Recently, 2D drawing on virtual canvases is increasingly being employed in many contexts, such as remote meeting or artistic expressions. The use of VR offers drawing on virtual canvases of arbitrary size and shape without physical constraints. However, this advantage is not fully exploited because of the need for physical surfaces such as desks for accurate and comfortable user interaction. Since the sizes of the physical surfaces are limited, the available canvas size in VR is also limited. One solution for such problem is to use encountered type haptic displays. These methods can adaptively provide haptic feedback of physical surfaces at arbitrary positions by using self-actuated robots or robotic arms. However, these methods depend on additional hardware, thereby leading to the problem of placement delay or safety risks. In contrast to the hardware-based solutions, a methodology called redirection can be another promising approach for addressing the physical constraints for VR drawing. Redirection is a methodology that visually manipulates the user's movement in VR, and its concept can also be applied to hand movements. However, no studies have examined redirection during drawing interactions. Therefore, we propose redirected drawing, a methodology for expanding the perceived surface size by visually manipulating the position or orientation of the user's hand while drawing. Unlike the conventional hand redirection techniques, redirected drawing has two assumptions. One is that the visual manipulation is applied only while drawing on a 2D surface in VR, and the other is that the manipulation is applied within a range that does not interfere with the drawing task. One of the most important design factors for redirected drawing is whether the system knows the user's drawing target, and we propose several methods for each case. Here is the design space of redirected drawing. For unknown drawing targets, constant visual manipulation independent from the drawing content would be ideal. Examples include translation game manipulation, where the stroke displacement in VR is simply multiplied at a certain ratio, or boundary-based resetting, where the system instructs the user to move the hand away from the boundary while temporarily interrupting the drawing task. For known drawing targets, the system can apply more purposeful manipulation. Examples include curvature or bending game manipulation, where the system guides the user's hand away from the physical boundary, or stroke-by-stroke shifting, where the system shifts the position of the user's hand at specific moments so that the stroke fits into the canvas. Among these methods, we specifically focus on translation game manipulation due to its high applicability. We conducted an experiment to evaluate the user perception and task performance of translation game manipulation. Specifically, we investigate the effect of different input methods for drawing: finger in mid-air, finger on surface, and pen on surface. Through the experiment, we aim to address two research questions. The first is the effect of existence or absence of the haptic feedback. We expect that the existence of haptic feedback would increase the noticeability and decrease the acceptability of translation game manipulation, since it would contribute to more accurate estimation of the physical hand movements. The second is the effect of intensity of the haptic feedback. Comparing the direct haptic feedback from the fingertip and indirect one from the pen, we expect that the direct haptic feedback would have higher intensity and stronger effect for perceiving the gains, which would lead to higher noticeability and lower acceptability. Combining these two research questions, we set these two hypotheses. Hypothesis 1 for noticeability and Hypothesis 2 for acceptability. The experiment had two independent variables, gains and input methods. Gains refer to the ratio of stroke displacement in VR and in reality. For the input method, as mentioned in the previous slide, we set three conditions: finger in mid-air, finger on surface, and pen on surface. For dependent variables, We measured noticeability, acceptability, drawing error, and task completion time. Due to the time constraint, please refer to our paper for details of the results of drawing error and task completion time. I'm going to explain the details of the input method conditions. The first is finger in mid-air, where the participants draw strokes by moving the index finger in mid-air. The second is finger on surface, where the participants draw strokes by moving the index finger on the desk. The third is pen on surface, where the participants draw strokes by moving the pen on the desk. Moving on to the results. First, I will talk about noticeability. The figure shows the psychometric curves in each input method condition, and the table shows the threshold values. We found that for higher gains, pen on surface was least noticeable, while for lower gains, finger in mid-air was least noticeable. Therefore, hypothesis 1 was not supported. We believe the main reason for lower noticeability in pen on surface would be the difference in drawing point. The drawing point in pen on surface was pen tip, which was slightly distant from the user's fingertip, leading to distinct user perception from finger in mid-air or finger on surface. This effect might have been more predominant than our initial assumption, the existence or absence of the haptic feedback. On the other hand, finger in mid-air was least noticeable in lower gains. We believe one reason might be the absence of physical support as we expected. In addition to this, we speculate another reason to be longer hand movement due to a lower gain. The participants might have felt increased task difficulty and fatigue, which made them distract from perceiving the gain. Next, I will explain the results of acceptability. Unlike noticeability, the acceptability scores were not significantly different between input methods, which did not support hypothesis 2. For the effect of gain, we found that the acceptability scores highly depend on the gains, but the trend was not entirely symmetric between lower and higher gains. That is, we found that lower gains tend to produce lower acceptability compared to higher gains. To explain this effect, we will focus on subjective discrepancy caused by gains. We define subjective discrepancy as the difference of the physical hand movement distance from the referential distance. Following the Weber-Fechner's law, we define subjective discrepancy as this equation. We performed a linear regression and found that the subjective discrepancy could reasonably explain the acceptability. Based on this estimation model, we found that gains between 0.78 and 1.30 would give acceptability scores above 3.0, which corresponds to somewhat acceptable. Here we summarize our results and derive usage guidelines. In terms of noticeability, using a pen on a physical surface is most recommended, where the stroke lengths can be manipulated up to 1.16 times larger without the user noticing. In terms of acceptability, the stroke lengths can be manipulated up to 1.30 times regardless of the input method. Furthermore, although I did not explain in the presentation, in terms of drawing accuracy and speed, the result shows that the use of a physical surface would be recommended. In this study, we proposed redirected drawing, a methodology that visually manipulates the position or orientation of the user's hand in VR while drawing strokes to expand the perceived canvas size. Among several possible methods for redirected drawing, we specifically focused on translation gain manipulation and investigated the noticeability, acceptability, and task performance under varied gains and input methods. The result showed that pen-based drawing was least noticeable compared to mid-air or finger-based drawing, where the gains up to 1.16 can be applied without the user noticing. Furthermore, we built an estimation model for acceptability based on subjective discrepancy, showing that the users can accept gains up to 1.30. In future, we will examine redirected drawing in more practical drawing tasks beyond line tracing, such as free drawing on a blank canvas. We also plan to implement smarter gain algorithms, such as adjusting gains dynamically based on the user's stroke speed. That's all for my presentation. Thank you for listening.